about what we call tinyML, or I would say to try to make very, very efficient AI processors for the edge, for the extreme edge. Now, what is this? Extreme edge devices are basically devices that we don't have, they don't compute in the cloud, they don't compute in our phones, but they really go to teeny tiny devices, watches, smart glasses, all kind of smart things in our environment that we want to be, or make them able to compute locally based on sensor signals they receive. And not by letting them send all these signals into the cloud and do all the artificial intelligence processing there, because that would be bad for latency, for privacy, for energy reasons. No, by instead allowing them to compute locally in the device different AI algorithms and create embedded machine learning. And that's something called recently with the term tinyML. And if this is a field that interests you, I really recommend you to go to tinyml.org. It's an organization, a non-profit organization that we started with a couple of people a few years ago, and now it kind of grew to a big community of people interested in tinyML, with weekly webinars and a yearly event in Europe and Asia and Silicon Valley, meetup groups across 40 countries or something. So very active field. I invite everyone to join. Now, why are so many people enthusiastic about this and working in this domain? That is because it brings together two different fields and creates many interesting challenges. On one hand, we have machine learning, which is already popular for many years, with all kinds of machine learning models, but now is quickly rising in impact through the wave of deep learning, deep neural networks that allow a myriad of opportunities, new applications that were not possible before. But these deep neural networks are super compute intensive. They really require lots and lots of computations, and that kind of blocks or is very difficult in these tinyML systems, these embedded systems. Because these systems are typically systems with only very small amount of memory, with very low energy budgets, yet they have to do real-time tasks, real-time applications. Have something in my environment is happening and I want to get that information immediately. So that creates a very interesting tension. I have these very difficult compute-heavy algorithms, and I have these real-time energy memory constraints. That's what tinyML is after, making that reality. Some people will say, this is already happening. I have tinyML because my face can do, my phone can do face unlock. If I talk to the phone, it will understand what I'm saying. If I have a car, it can do lane assist and all kind of intelligent behavior. And I can already even buy smart glasses and do some augmented reality. To a certain extent, it's true, yet I will say or tell you that this is not really good enough. It's not what we actually want or need. Because yes, my phone can unlock with my face, but that's like the simplest machine learning task you can almost think of, with just recognizing one face. And yes, I can talk to the phone, but the phone only detects that I say, hey Siri. Everything else is still sent to the cloud to do my big speech processing somewhere on the server of Google or Apple or whoever. And yes, my car can already do some lane assist, but it's very far from doing actually self-driving. And these smart glasses, they can do some simple tasks and some augmented reality, but most of the time with a big bulky battery on top, or after 1 or 2 hours, their battery is gone. So we're not there yet. Now, let's try to understand what it would take to get there, to really enable some of these applications. And for that, I'm going to do some back of the envelope calculations. And they're very naive, but they put us, at least give us a baseline number. And I'll do it with the two applications we had in the bottom. And let's start with a self-driving car or a smart car. If I'm very naive, I just say, okay, let's assume we have 6 cameras, a couple in the front, couple in the back, to the sides. They run at 30 frames per second. And let's naively assume I want to do one ResNet 50 network evaluation on every frame. ResNet 50 is a neural network. It's not a very big one. It's also not a tiny one. It's definitely not good enough to do self-driving, but it's just a baseline network that I take. Let's assume we do this on every single frame. It's an underestimation. And then let's assume we have 10 watts to do the processing of this ResNet 50 on every frame. And why 10 watts? That's basically what's allowed to put in terms of compute heat and power behind the glove compartment of your car, which is where this compute box typically sits. If you do that and you do the math, you will see that you need about 300 giga at 10 to the power 9 operations per frame, and hence about 1,000 tera operations per, 100 tera operations per second. So 10 to the power 14 operations every second. Okay. And if you want to do that with 10 watt, it is 10 tera operations per second per watt. And we say 10 tops per watt, typical metric that's used in machine learning. Okay, we'll see later whether that's feasible or not. If we go to the smart glass, what you see, of course, you need less cameras, but I also now have a smaller power budget, only about 100 milliwatts or even less. And you see, now I only need about 10 tera operations per second, but my energy efficiency constraint goes up. I need roughly 100 tera operations per second per watt. I have to be more efficient in my compute. These numbers, 10 tops, 100 tops, 100 tops per watt. Is this difficult? Is this easy? Well, let's see. What you have here on the x-axis is the power consumption of my device. On the y-axis, you have the throughput, operations per second. Means that the diagonal lines are the energy efficiency. How many operations can I do per second per watt of power consumption that I invest? And I put the 2 dots of my application that I just did the math for you. And now let's see what exists. First of all, we have GPUs. Every green dot is a GPU implementation that you can commercially buy today. On the top, you see the big GPUs. They get the throughput we need, but not at the power budget we have. And on the bottom, you see the embedded GPUs. They're much better in terms of power consumption, but they don't get good enough throughputs. So GPU is not good enough today for this application. People develop all kinds of interesting systems on FPGA. And yes, FPGAs can make a clever design and more computes or customized hardware, but an FPGA in itself is not an efficient platform. There's too many switching matrices and routing blocks, and it's also not a power efficient solution. But then the field of machine learning has the last decade been sprawled, and there are so many customized chips made for AI processors. Every single dot here is a published chip that has been optimized to do AI processing in a custom processor, an application-specific integrated processor. And you see they boost efficiency by a factor 100 or even more, get much closer to these red dots. Let's take a look at what these things exactly do. What are the tricks that all these dots are using? And some of the dots are coming from my lab, so I'm going to give some examples based on things we built. And I'm especially going to use the Diana chip. That's the one you have there in the middle. So in this talk, I'll first talk a bit about what are efficiency techniques in machine learning processing, then talk a bit more about Diana, and then we'll refer to scheduling because a new challenge is popping up there. So to understand what an ML processor is, or basically why it's better than this GPU or CPU or FPGA implementations, we have to understand a little bit what the workload is. And I'm going to simplify it a bit here, but a typical machine learning workload in a bit simpler way, you can say it's just doing big matrix multiplications. I have a big input matrix, I have a big weight matrix, and I have to do all my cross products to compute a big output matrix. And what's important to note here is that hence every row of the input is used in many columns of the output and multiplied with many columns of the output, and every column of the weight of the, every row of the input is multiplied with many columns of the weight to create different outputs, and every column of the weight is also multiplied with many rows of the inputs. So there is quite a lot of data reuse opportunities. We're going to need that later. To do this matrix multiplication, a typical machine learning processor, first of all, has a data path equipped with many processing elements. And it can really be thousands of them. And every processing element is, in essence, a multiply accumulate block, a multiplier and an adder, with some local registers to store data locally, inputs or outputs. Of course, the data path has to be foreseen from data, so there is on-chip a memory hierarchy with one or more levels of register files and SRAM to feed data into this data path. And typically, that memory is not even large enough to hold a complete network, so that network or that memory hierarchy is again fed with data from an off-chip DRAM. Now, if you're thinking that you want to make this processor efficient, you first have to see where the energy goes in such a processor. And for that, let's see that first of all, the data comes from the off-chip DRAM. It has to be brought inside the on-chip memories, the SRAMs, will cost me some energy. From there, be brought into the data path, will again cost me energy. Then I have to do the compute, multiply, accumulate, and we also call it a MAC. I'm happy to spend my energy there. This is what I actually want to do. Everything else is overhead. Then I have to bring the result back into my on-chip memory, and finally my off-chip memory. If you want to optimize the efficiency of a neural network processor, you have to optimize the sum of all these components. Many people focus on pushing the energy per multiply add down and make super efficient processing unit. Then you have not really solved the problem. The left part is probably consuming sometimes even 10 times more than just a multiply add. Unless you do a clever design, then you can balance it better. So what is this clever design that people do? What are the tricks we can play in this field? Everyone uses the same tricks, just to different extent and with different flavors. So the first thing you can do, and that everyone does, is you can play with the precision of the neural network processing. If I have to do memory transfers, and I have to transfer 32 bits of inputs and weights and outputs every time I go from one memory level to another, costs me much more energy than if I can just transfer 8 bits or 4 bits at a time. And of course, also in my compute unit, computing at lower number of bits helps me for my energy efficiency. So neural networks typically do not run in floating point precision, definitely not in high bit floating point precision. And there is a lot of research in the algorithmic community on trying to bring the precision of neural network processing down as much as possible. And I think the most interesting field or findings in this are training algorithms that do not just allow to train for low bit precision, where I can say train the whole network at 4 bits. That's already a bit old school. Now what people do is you train the neural network, and during the training, the network itself figures out what the best precision is for every single layer. This works with differentiable architecture search, where basically in the beginning, every layer has a representation of multiple options of different bits, a 1-bit option, a 2-bit option, a 4-bit option, 8-bit option, and the network learns which of these options to keep. Let me take a pointer. This is also going to help. Which of these options to keep, and which of the and only one option kind of stays and everything else gets suppressed. And if you do that, you get results like this, where, for example, it's a bit small, but the top is a RZ50 network, and you see the number of bits the network learns to use for the weights on top, the activations in the bottom, and every bar is a different layer of the neural network. And you see the first layer needs 4 bits of weights, 4 bits of activations. The second layer needs 1-bit weight, 3-bit activation, and so on and so on. So every height of the bar says how many bits. So you see, and the same on the bottom is here for an inception V3, a bigger network. And you see, every single layer needs a different number of bits for weights and a different number of bits for activations. Of course, I'm not an algorithmic designer, I'm a hardware person, but this has implications for me. It means that I have to build a processor that can basically process dynamically from layer to layer at different bit precisions. We explored this, it's an older work, but we explored this already in 2017, where, for example, the Envision processor that we taped out had processing elements that you see here that natively worked at that time at 16-bit precision, so 16-bit input, 16-bit weights, but they could dynamically be split into 2 8-bit parallel multiply accumulate blocks or 4 4-bit parallel multiply accumulate blocks, and so on. This is old work. Since then, many different precision scalable processors has been published. And I think nowadays, almost every neural network processor has some form of adjustment or possibilities to scale precisions. The big question, though, open question is, should we just make one processing element like here that can, inside one element, support all different precision modes? Or should you, and this is work from IBM last year, instead have parallel data paths where you support different precision modes in a different functional block? For example, the IBM processor has a separate functional unit to do 16 and 8-bit floating point operations, and then another one that can do 2-bit and 4-bit fixed point operations. And they deliberately kept them separate because it resulted in more efficient solutions, energy efficient solutions. Of course, it's more energy efficient, but it's less area efficient. Now, at least one of my data paths is always idle. So there is a trade-off here between efficiency, area investment. We're going to come back to that later in the talk. Second trick that every single neural network processor is exploiting is to exploit data reuse. I already told you earlier that every column here, every row on the input is multiplied with all the columns of the weights. And every column of the weight is multiplied with all the rows of the input. And every output pixel here is an accumulation of many different multiplication operations. So you have a lot of data elements that are repeatedly used. You can exploit it in your data path. Instead of fetching a separate input and a separate weight for every PE, I can fetch a weight once and use it across a whole row or a whole column or a diagonal of my processing element matrix. And that saves me a lot of energy because I still have to do the same operations, but I now have to fetch much less times the same data value from memory, and that will bring down my energy drastically. Now that data reuse is exploited also in almost any neural network processor. And if you look at it, it's typically, or there's many options or ways in which you can do that. And to see how people exploit this, it's always good to look at their nested for loop representation. Every matrix multiplication or every convolution operation, which is where I have an example for here, can be written as a big set of nested for loops. And most of these for loops you will execute temporally. You will over time go through the different rows and the different columns here. But some of the for loops or some part of the for loop you can execute in parallel, not spatial, not temporal across clock cycles, but spatially within one clock cycle. And we do that by replacing a loop by what we call a par for loop, a spatially unrolled loop on the hardware. In this case, my input channels and my output channels are spatially unrolled on my data path, which means that every input here and every weight can be reused across rows. Outputs can be accumulated across columns. I have my data reuse opportunities. Of course, this only works well if the workload that I have nicely fits my array. If this is an array of 16 elements vertically and 16 elements horizontally, and I have a matrix that is a nice multiple of 16 in its dimensions, it is perfectly using my data path. In reality, however, many many neural network layers have various different shapes and topologies. I have some with few channels, I have others with many channels, few input size, large input size. And the result is that some layers will be able to perfectly use my array, fully have 100% utilization of every processing element. And other layers, they don't have enough parallelism in the specific dimension that I use here spatially, and they will keep part of the multipliers idle. That's again a big waste. It's a throughput waste, it's energy efficiency waste. And we have to avoid that. And you could again avoid that by, in one data path, not only support one specific type of spatial unrolling, one specific data reuse way, but for example, by having reconfigurable data paths that support multiple different types of parallelization. And for one layer, I do my channels in parallel. For another layer, I do maybe my input pixels in parallel, and so on. But of course, this again costs some overhead. Reconfigurability always costs us energy and area. Yeah. Okay, so this is for something we tried in the Depfin processor. It's a processor from 2021, where we had a huge data path, 128 columns, 16 rows, so in total 2048 multiply accumulate blocks in one processor. And of course, then it's hard to keep it busy, but this data path, without going in all the details, had quite some configurability inside to either map a depth-wise layer and in parallel a point-wise layer on the same data path, or do a 3x3 convolution or a 1x1 convolution, and all kind of combinations to keep the data path as busy as possible for many different workload topologies. Other people again approach it in a different way, where they say, no, it's hard to make one data path have good utilization for all types of layers. We just put many different data types with different parallelization strategies next to each other. Data path 1 parallelizes in this way, data path 2 in another way, data path 3 in another way. And this is then a multi-core accelerator, and I just send my layers to the accelerator that fits best. Again, this will be more efficient when you use the specific block, but many of these accelerators will be idling when I'm maybe using accelerator 3 because it's efficient. What are accelerator 1 and 2 doing? So it's again a trade-off between efficiency and area. Come back to that. Now I told you about trick number 1 and trick number 2. It's now interesting to think, can we push this to the extreme? Can I go with very low precision? Can I go with extreme parallelization and data reuse? And that is something that people are actively trying when they go for in-memory compute. In-memory compute is a new trend where you bring together compute cell or compute capabilities inside a memory, typically an SRAM memory, but can also be resistive RAM, PCM, and so on. And how we do that here is we make a very big array of memory cells, maybe 512 rows, 512 columns, so 1 million cells almost. And inside every memory cell, we store the weight elements. So we store the different entries of our weight matrix. And then on every bit line, on every word line, so on the rows of the memory, we activate the bit cells through or with the inputs that comes from our input matrix. So I basically will stimulate every weight on this row with the top input, with the first element here, and then the next one with the second element, and then the last one here with the last element of this vector, basically. And if you stimulate a memory cell with a word line and you design it in the right way, it will put on the bit line, so on the vertical line, the multiplication of the impact of the weight of the red element and the blue element. So there will be a multiplication operation taking place inside the SRAM cell. The result of that is pushed in terms of charge or current on the purple bit line. And now this bit line nicely accumulates the contribution of every single element here multiplied with every single element here. And here at the bottom, I can put an ADC and get my multiply accumulate output. This is computing in the analog domain, can be extremely efficient, and especially massively parallel. So 512 rows, 512 columns. My data reuse is enormous. I can compute very efficiently, not at high precision, at rather low precision, but with stellar tera operations per watt, you could say. But it's not all happy news. The problem is, though, there is no flexibility or almost no flexibility. I have massive data reuse if my matrix, if my workload is big enough to use the complete array. If the matrix multiplication I have to do is smaller, then a big part of my memory will be idling. Again, a waste of my energy, a waste of my throughput. If I need higher precision, it's also hard. Doing very good 8-bit computation in the analog domain, we haven't seen many designs reaching that. So that brings me back to the graph I had here. It was very interesting to see that many of the dots on the graph are coming close to my red balls that I want to realize. But now we have to understand that many of these dots on the top, they're this kind of massive data paths and in-memory compute that exploit big data reuse, great efficiency, wonderful. But these are peak workloads that people publish. This is the precision, this is the throughput and the power efficiency they get when they load the whole array with a nice matrix that perfectly fits the accelerator that they published. It's not actual workload performance. So actual performance might be a bit lower. It depends on how flexible these designs are. At the same time, and this is the same graph, but now the labels here indicate what precision the different blocks compute at. You see that all these very efficient designs, they compute in the binary, ternary, 2-bit precision. They have very low computational precision. Again, great, you get good efficiencies from this, but it doesn't work for all network layers. Some still need 4-bit precision or 2-bit, 3-bit precision, and so on. So that's what we see. It's great. We can push up this curve to the top left. That's where we want to be by playing with precision and data reuse. But it works very nice for the peak performance. Don't forget your workload performance. To get good workload performance, we need flexibility. Unfortunately, the flexible designs, they are more here in the bottom. So the quest now is, can we make a design that is good and efficient when it can really exploit this massive parallel low precision compute, typically the middle layers of my neural network, but that still has the flexibility to also efficiently deal with the first layers of the network, the fully connected layers, all the layers that need higher precision, different data flows. And that can even maybe still do also the post-processing by subsampling, all other kind of neural network functions that we often forget, pooling, batch normalization, and so on. So that was the quest we're after with when we designed Diana. Yes, we want to exploit analog in-memory compute for the layers that can really benefit from it, but we need enough flexibility to also cover all the other layers. So in the Diana system, we went after this by making a very heterogeneous multi-core system. So on one hand, we want a CPU that can do all the pre-processing, post-processing, and manage the rest of the system. We also want a very efficient analog in-memory compute block that can very efficiently process these very widely parallel low precision layers. But in the middle sits also a digital, more traditional AI processing core that has the flexibility of different data flows, can compute at high precision, medium precision when needed, and so on. So this resulted in the following SoC. On the left, there is a RISC-V processor, our host, connected through a bus to a shared memory that it shares with two accelerator cores, a digital accelerator core with a 16 by 16 processing element array, and an analog accelerator core with an in-memory compute block. And so by combining all these three aspects, and especially by playing with the memory hierarchy, how all these things can share data, we now have a very heterogeneous system and you can optimize what layers you run where. Before I show you how we schedule workloads on there, let's quickly or briefly dive into these main blocks. We took from Luca Pianini, the Opissimo platform. I won't go into detail there. The digital core is a typical digital machine learning accelerator. It has a sea of processing elements, all multiply 16 rows, 16 columns. Every processing element can compute at 8 bits, or it can do 2 parallel 4-bit computes or 4 parallel 2-bit computes. And it has all the flexibility to do all different kind of layers, very wide data flow flexibility. Then the analog core that's here is the one that we want to massively push for efficiency. So it's a core that has 512 by 1152 PE elements, so SRAM elements, you should say. So it can do a ternary compute of 500,000 multiply accumulates per cycle. The weights are ternary, so 1.5 bits. The activations are 7 bits. So it's a mixed precision, a higher number of activation bits than weight bits. On the bottom, there is a SIMD block for all the post-processing. Now, this accelerator, we wanted to push it for maximum efficiency. It means we have to keep it busy all the time. So the system is designed in a pipeline fashion so that always useful compute can happen, which means that, first of all, data is prepared for the next compute cycle in our data loading stage. While that is happening, the data from the previous stage is already inside the in-memory compute array to do the processing there. And again, in parallel, while this is happening, the data from the stage, even one before that, at a cycle before that, is in the SIMD post-processing block to do all the other types of layers. So it's really in a pipeline fashion. The data moves stage to stage so that every compute unit is as busy as possible. In this SIMD stage here in the bottom, we have the flexibility to run basically the different things you do after you do the matrix multiplication. So partial sum accumulation, batch normalization, residual additions, activation functions, values, and so on, requantization, and then the pooling operations. This also happens in parallel because it has to swallow all the data that comes out of the big multiplier array. Now, if you design these blocks, we're not fully there yet because they have to be able to efficiently exchange data. They have a big level 2 shared memory, fine, but that's not a very efficient way of sharing data. It costs a lot of energy and time to push the data up and pull the data back in, especially because the bandwidth of this bus is not that high. So the two accelerators also share a local memory where each of them can read and write into a multi-banked memory. Now, when they do that, of course, the data format of the digital core would have to be the same as the data format of the analog core. And unfortunately, that's not the case. Because the digital core typically, if I go back here, the digital core computes pixel parallel. It means the different elements of the x dimension of my matrix is what I put on the horizontal dimension here, is what's shared in parallel. So I have to put the 16 different width values of the matrix into the array. The in-memory compute block is different. It needs the different elements that accumulate to one output together at the input. So it's my fx, fy, and c, if you're a bit familiar with convolution. So they need different type of data in parallel into the data path to compute. And that's annoying, because as long as I'm computing on the digital data path, it's fine. For my shared memory here, I push my data pixel parallel into the array, I can pull it out pixel parallel, and I can keep computing here. If I only compute on the analog core, it's also fine. I push the data in channel parallel, it computes, data comes out channel parallel. I can keep computing on the analog core and store the data in between. But if I run one layer on the digital core and the next one on the analog core, then my data format has to change in memory. Now that's possible because we made the digital core flexible enough so that it can read out the data pixel parallel, but it can also read the data out channel parallel. So if the digital data path knows that the next layer will run in the analog domain, he pushes the data out in another fashion, sends it into the shared memory, and then the analog core can work with it. In the other direction, if a layer runs on the analog core and the next one on the digital, the analog core is not flexible enough to do that transformation itself. There is a small reshuffling buffer that changes the data format and pushes it back to the digital core. Now, we end up with our chip, and we can now start to measure its efficiency. And what you see here is, first of all, the measurements of the digital core. This is measured at the system level, so we measure the power consumption of the whole chip, including the RISC-V, all the memories, everything together. But at the moment that only the digital core is computing and everyone else is idling or waiting. And you see then that the digital core is able to get up to, these are the bars, about 2 tera operations per second per watt, and running at, and this is the orange line, a throughput of 0.1 or something tera operations per second. Okay, fine. This is the first part of the system. If I then do the same measurements for only the analog core, you basically, again, see the analog core here on the left. It now gets 200 tera operations per second per watt, so about a factor 100 better than the digital. And also in throughput, the orange line, it's 10 tera operations per second, so also about a factor 100 higher than the digital core. So the digital core and the analog core differ roughly a factor 100 in throughput and energy efficiency. Now, of course, be careful, it's an apples and oranges comparison. This thing runs, or at least for these measurements, at 8-bit precision of weight, 8-bit precision of activations. This thing runs at ternary precision of weight and 7-bit precision of activation. So it's not doing the same operation. But still, we can exploit it. Roughly a factor 100 difference. The question is now, how can we use this? How can we map neural networks on there? Scheduling problem. First of all, we are also working with the University of Bologna on training now neural networks that have part of the layers in this ternary format, part of the layers in the 8-bit format. I didn't bring it to this. Talk, but basically assume we can use that kind of training. The question will boil down to, okay, this is my system. I have my RISC core, my digital core, my analog core. For my neural network, which layers do I want to map in the digital domain? Which layers will I map on the analog core to the most efficient execution? The question are basically, you have to figure out how expensive will it be to run this layer on the digital core, or how expensive will it be to run this layer on the analog core. Even if you build a training algorithm that can figure out what layer should run in what precision, it has to have information of how expensive the decision of that training algorithm is. Is it factor 100 different or 10 and so on? I showed you here it's a factor 100 difference, but this is Of course, it changes for every workload. Some workloads use one core a bit more efficient, others use another core more efficient. These were peak performances. To get that estimation better for every single workload, we have been working already for quite some time on a cost model and design space exploration framework. And it's called Zigzag. By the way, it's open source. Everyone can download it and use it on GitHub. It has a tutorial also now, a user guide, which wasn't there before. So the goal or the inner working of this thing is a cost model that takes in, on one hand, a neural network workload, so a definition of my neural network model. It takes in a definition of my hardware architecture, can be my digital core, can be my analog core, different variants of it, and it takes in technology information. And with that information, it maps the neural network workload on the digital and analog core. It means it figures out how are the for loops, what are the temporal orderings, what things do I do in parallel, so which loops do I make these par for loops, and so on. And for a given mapping, it can then compute how much energy, latency, and area or memory will it cost me to execute this workload on that processor. And of course, wonder, is it accurate, the computations you do? Well, we try to benchmark it against several chips that we have both measured in the lab as well as simulated in our team. And you see the model and the model, so Zigzag, and the actual measurement, either post-synthesis or really measured in the lab, is typically within 5–6% of accuracy. Not perfect, but definitely good enough to make relative decisions and these scheduling calls. Now, of course, once we have such framework where we can trust what energy and latency predictions it make, we can use it to do some optimizations, to use it in an iterative loop. The first thing you could optimize, you could iterate, is the mapping. Because for a given neural network workload and a given architecture, there is many different ways in which I can schedule that workload on that hardware architecture. And these many different ways really make a tremendous difference in energy efficiency and latency efficiency. So you can really play with how you map it and use a different mapping if you care more about energy, you care more about latency, or a combination of them. Without going into all the details, Zigzag has many different types of mappings and also something called uneven mapping. And uneven mapping means that you also smartly allocate your inputs, your weights, and your outputs to different levels in the memory hierarchy. And the weights can use other levels of the memory hierarchy than the inputs and the outputs. So you can really play with what do I store where to maximally use this or maximally do data reuse and tiling of my workloads. And if you do that, you see these very nice trade-offs between utilization, so that's throughput of my array, and then energy efficiency. And we can do that for the analog and digital core, and based on this decide which core has the best utilization for this workload, which core is the most efficient. Now, that kind of optimizations are, of course, after I taped out my chip. I have a chip, I can now optimize the scheduling, fine. But Zigzag can also be used at design time. You don't have to wait until the chip is taped out to use it, because the same tool can be used to now start to modify the hardware architecture. What if I have a bigger in-memory compute block? Or what if I have a smaller memory? What is the impact on the throughput and the energy efficiency of my whole system? And we, for example, use that to find out how large we should make the in-memory compute array. It is 1,152 by 512. Well, it's a trade-off optimization that we did for different compute memory sizes. We played with different activation memory sizes, and you get this trade-off between tera operations per second per millimeter square and tera operations per second per watt. And the trade-off is different for every neural network you run. Your conclusion will be that there is no one optimal design that is good for all different networks. But this area was pretty close, or this thing was pretty close to the Pareto curve for most big networks. But you can use it to figure out all kinds of other hardware configurations. Now, once you have your design, you have your scheduling tool, we can then map this layer in analog, that layer in digital. But you will quickly see that if you just do it in a naive way, your system will be used very inefficiently. Because if I run the first layer on the digital core, second layer in analog, third layer in analog, and I just run it layer by layer, so the analog is waiting for layer 1 to be done, and then it starts to compute, then my cores are like idle more than 50% of the time. This one is doing nothing here, this one is doing nothing here. What a waste. Can we not use the cores more efficiently? And it turns out you can, because you don't have to wait until this whole layer 1 is done in digital before the analog can kick off. Because of localized computing convolutions, I can compute part of the green layer, already send that result to the red layer, and the red one can start to compute while the green one is finishing off the rest of layer 1. And then layer 2 and 3 can go on in parallel while layer 1 is still ongoing. And this pushes up the utilization of your hardware a lot. Of course, brings a latency benefit, but that's not even the biggest benefit. And let me illustrate this with this ResNet example. That we run these layers in digital, those layers in analog. Yes, my latency improves because I overlap my compute. But more importantly, my memory footprint of my compute drops. Because instead of having to store a complete layer and pushing that complete layer to the next block, I now only have to store a fraction of a layer. And I push that fraction of the layer to the next block that immediately consumes it, and I can forget about that data because I can use the same memory footprint for the next batch of data. So this brought down our memory requirements for activation memory to do the compute by a factor 5. Factor 5 sounds nice, but it's even more important than just a factor 5 reduction, because the original memory footprint didn't fit my small L1 memory. It didn't even fit my shared L2 memory. It could only be fetched from off-chip DRAM. Super expensive, super slow. But with this optimization, I can now just store my on-chip memory, my data in my nearby memory to exchange between analog and digital, and I never have to go back to the big memories. This gives much more than a factor 5 throughput benefits and energy benefits. But, and that is the big challenge now, it increases your degrees of freedom for scheduling enormously, because now I don't have to just schedule when I have to schedule when I execute which fraction of which layer on which core. And this results in a much larger degree of freedom and optimization space for scheduling. And here I have a very stupid Mickey Mouse example of a neural network with 4 layers executed on 3 cores. I also have my bus and my DRAM bandwidth that I have to schedule the traffic, the dynamic traffic on. And then every single small snippet can be scheduled individually, great. But you have to figure out the most energy optimal or latency optimal schedule, for example. Zigzag has been extended to be able to do this. You can then ask him, give me the best latency schedule. And I see layer 1 goes in the digital core, layer 2 in the in-memory core, some stuff happens on the RISC. They exchange all kind of data on the bus here. And this is the memory they use in the L1 shared memory. But I could also say, no, give me not the most latency efficient solution, give me the solution with the lower memory footprint, below a certain threshold. And then you give me a solution that consumes a bit more clock cycles, but uses less on-chip memory. Maybe because there is not that much available. This was for a Mickey Mouse example, but we have the same for the Diana chip. So this is our Diana chip. This is the ResNet workload we map. And you can now see layer 1 is very big, happens still on the digital core, and all the other layers on the memory core, some SIMD processing. And this is how much memory every single core uses across time throughout the execution of this to see that it still fits the L1 memory. This all sounds like good news. You can keep all the cores busy. You can schedule. Zigzag can keep the utilization high. Is this chip all good news? No, we also learned a lot from it. And I'll show you some of the bad news because that's where we can improve for the future. Everything I showed you, yeah, it's a complex graph. So I'll walk you through and then I draw the conclusions. Here you see the latency for different layers of a ResNet network. The first layer runs in digital together with the pooling. All the other layers run in the analog in memory compute. Every bar says the execution latency, and it's split into 2 or 3 parts. First of all, you have the compute, the pink part. That's great, digital compute. Analog in memory compute is very fast because it's super parallel, very wide parallelism. But then the green part is the data movement. Because this first layer is so large, the input of that first layer has to be drawn into the system. It still consists of a lot of data movement. Also the pooling, because you have to do data reduction, doesn't fit the L1 memory. And then if you go into the deeper layers, we can exploit this fine-grained parallelism, we have a bit less data movement, but now the weight loading becomes quite heavy because it's great that you can do in-memory compute, super efficient compute, but it assumes the weights are already in the SRAM array. But you have to bring these weights into your array first, and the more you do the fine-grained tiling, the more you have to constantly move weights. And my compute becomes efficient, but my weight movement is now just taking up all my latency. And by the way, also this is the same graph for energy, also my energy. And the result is that the dashed lines are the efficiency, the dashed lines for latency here and here for energy. You have to look at the right graph for the dashed line. These are the efficiency, the throughput, and the teraops per watt of my core compute, my digital array, my analog array. And this is very high. This is close to the maximum efficiency that my analog array can really achieve, especially this res block 512. It perfectly uses my array, gets my peak throughput. But this is the efficiency of the array itself. If you also take into account all the energy and latency that goes to data movement, then you get the system level efficiency. Then you get this blue line here for throughput and the blue line here for energy efficiency. It's still not bad. It gets 2 teraops per second on average for a whole actual, not peak workload, but an actual ResNet workload at the system level. And here, couple 10, 20 tera operations per second per watt. This is a good number if you compare it and know that it's a system level actual workload number. But still, what a waste, what a big difference between the dash bar and the actual system efficiency. And of course, this is because we underestimated some of these data traffic issues. Now Zigzag models them all. We see why it's bad, but by the time we made the chip, our modeling framework didn't have all of these yet. For example, our SRAM block has a very small weight bandwidth. So it takes us many, many clock cycles to fill the weights in the in-memory compute block. So just to call out to the community, to you, we should not just care about compute efficiency. Everyone gets that high. That's okay. Peak workload efficiency is easy to get. You should also care about system efficiency. How do you move data from one core to another? How do you move the weights inside? What do you do with post-processing, the SIMD, the pooling? How do you efficiently do that, the batch norm, and so on? So, end of my talk. With open questions, open challenges we can all work on. Most important message I wanted to give is specialization is important. Custom AI processors are here to stay. You need flexibility and you also need efficiency. So that's a call or a good opportunity for heterogeneous workloads or heterogeneous systems where you have different precision modes you can support, different data flows, but you have to realize that this makes your design space exploration more complex, your scheduling more complex, data movement starts to be an important part of the problem. So there is some interesting stuff done, but still many challenges ahead, and I think it's a very interesting system level optimization problem. Thank you.
So thank you, Marian, for this wonderful talk. So now the session is open for questions. If you have some questions.
Really, thank you for your nice talk. I have two questions. The first one is, I guess in the page 13.
13.
You set the value of 1.5 as the scaling energy scaling factor,
yeah.
Exponential and back.
Yeah.
How can you estimate the value?
So the 1.5 is an approximation. What we know for sure is it's not linear and it's not quadratic, but it's somewhere in between. And that makes sense because in a multiplier, your cost is roughly quadratic. In an adder, the cost is roughly linear, logarithmic, and you make a kind of combination of the two. So I put here 1.5 to put the general guideline. In our actual modeling framework, we just characterize the cost of different precisions through some hardware simulations, so some post-synthesis simulations of different precision levels. This is a rough guideline. Of course, if you design it, it is a bit more, a bit less. Depends exactly on how you implement it. But it's for sure between linear and quadratic.
Okay, and next one is the page 53. In resonant 18 determinism, what are the digital computation parameters for residual block 64?
Ah, yeah. Yeah, indeed. So there are some digital computation blocks also here. This is the SIMD unit at the bottom. So this is everything: partial sum accumulation, batch normalization, bias addition, requantization, pooling operations, everything you do after the multiply accumulate. And also that people sometimes forget, I have a great in-memory computer array, and then I have to do the post-processing. That post-processing, you see, if you start to accelerate your multiplications well, they disappear, everything else becomes the bottleneck. So that is the digital computations there.
We have another question. We have time for a few questions.
Hi, thanks
Hello.
very much for the nice talk. So I have a question about the system level efficiency. How, in this estimation, how did you estimate the memory access part? Because it may contain DRAM access, DRAM memory controllers, lots of other systems.
So in our modeling framework, we do estimate all of that. So what the framework basically does here is from the scheduling, it identifies which data sits in which memory. And you do that from starting from the inner loops, and you see what fits in my register file. And when that's full, the next layer is local SRAM. When that's full, the next 4 loops go into a global SRAM. Or a DRAM, and you can shuffle the loops around until you find an optimum. But once you know this allocation, you can perfectly analytically compute how many memory accesses, both read and write, you have to do to every upper level. And with these analytical estimations, as we know the bandwidth of our system, as we know the bandwidth of all this memory traffic, then we can compute the latency based on the number of accesses and the energy per access. We also know, so we can multiply the number of accesses with energy per access. So it's a pure analytical compute, simulated, psychoelectrically simulated.
Okay, so I understood. So it's like benchmarking the, using the ops per joule or memory access per.
From the workload, we compute the required number of memory accesses. From our hardware, we know the energy per access that is needed and the time per access, and this allows us to integrate all of this into an effective number of ops per joule and ops per second. Yes.
Thanks very much. And I really agree that it is the essential problem for the question of managers. And how do you, prospect for the future? The ML workloads becomes larger, this problem will increase or increase.
Yeah. No, I fully agree. I think what we will have to do for the future is to go to even smaller tiles. Yeah, so there is a separate problem for your weights and your activations. Maybe I should start with the weights first. For the weights, the main message for the weights is, yeah, we should have more compact networks. Okay, fine. We have to tell that to the algorithmic guys. But for us, we should basically make sure the weight loading bandwidth is very, very high. So if you have an SRAM, don't write your weights with a 32-bit or a 64-bit bus. You should really be able to massively dump weights from DRAM into SRAM. So it will just require many pins. It costs you energy, but it's okay because you only seldomly update these weights. You just have to be able to be very, very fast. For the activations, we have as hardware designers much more room to play because there we can really go with this very fine-grained tiling and move smaller chunks of data from one core to another. And there I think we can get activation memory down significantly. But this for me is a hardware problem, which I find we're also looking into this. But I think that we can solve. The weight, you have to compute this weight, these networks are so big, they have to come from DRAM, then it's a matter of bandwidth. Maybe 3D stacking can help us there with much wider bandwidths.
Thanks very much for the answer.
Okay.
You're welcome. Another question, maybe? Yeah.
Thank you. I have, I would say, just curiosity questions. From my point of view, you have two cores, an analog one and digital one. Do they have the same clock? Do they work with the same speed?
Very good question. All the digital works at the same speed, so including the digital periphery around the analog core, but the analog compute macro itself works on a slower clock. We can configure how much slower. Typically, we put it about 10 times slower. But let me quickly go to the analog core. It works out pretty nicely because it's doing 500,000 things in parallel anyway, so that's not the throughput or its clock speed is not a bottleneck. And the problem is, if we don't underclock it, then it would spit out every clock cycle 512 parallel results that we then have to post-process in this digital post-processing block. I don't have the area to put 512 parallel batch normalizations, residual additions, and so on. So we only have 64 of those. But if we have 64 of those in 8 clock cycles, we can just cycle 8 times through the 512 results. 8 times 64 is 512. So it's great. This thing works at the nominal clock speed. The core works 10 times slower, so we have some margin on processing it, and we're ready for the next batch.
Okay. So it fits quite nicely, and it's quite a bit of luck, or?
That's a good question. I think we thought about it. I think the basic point is, if you make the analog core faster, it doesn't help. That compute is not a bottleneck anymore. The digital cannot swallow it anyway. So they did that. I didn't design the analog core. We got it from IMEC, and we got it with this clock speed, and we said, oh, it's good enough. Okay. So,
Basic question. I'm sorry for just a short one. It looks like focused on inference. It was not clear for me, but it's.
Yep.
And how do you have ideas about applying this for learning? So computing gradients.
Yeah. Good point. Indeed, we focused on inference because it was. Definitely, we should push this further. What's changing in inference? I think two things. On one hand, again, different data types. You need FP8, FP16. You can extend this, I think, with again more heterogeneity for data types. The other part is different data flows. You have to do the backward computations with the transpose. You have to store your activations locally. That is the bigger problem because you have even more memory traffic. All the activations have to be retained in the forward pass to then go the backward pass. Scheduling will again be a big issue there, and a lot of local memory that's available at high bandwidth. Another challenge. I think definitely one people should look at.
Thank you very much.
Thank you. So now it's time to thank Marian again for this talk and for also the level of the questions. Thank you very much also. So thank you very much, Marian.
Thank you.